All right. So I'm going over the first part of this chapter 5. The subject of the chapter is equilibrium of rigid body, and we'll learn about condition equilibrium, free body diagrams, how to generate free body diagrams. Really important concept in statics. So shown here is an isolated body that's acted upon by forces and moments, four of them and two moments. And condition equilibrium is for these forces uh, together, that is sum that's vector to be zero, and sum of moments, couple moments, where the moments of the forces, including the directly generated couple moments, to be equal zero. So when you evaluate the forces of these moments, you pick a point, an arbitrary point, sorry. And so, yeah, these are the conditions of equilibrium. Sum of forces equals zero, sum of moments um, about an arbitrary point O to be zero. It's explained here that any point that is considered to evaluate moments should likewise give you the sum of moments as zero as a condition of equilibrium. So if this second equation is satisfied, if I set up sum of moments about point A, then I recognize that that's the sum of moments about the initial point O, and then the moment of the resultant um, about point A. And since this is zero and R is not zero, we have it has to be zero, the new sum. We're assuming that bodies remain rigid, that is, do not deform, although we'll see ropes and springs that deform, but we usually analyze rigid bodies in the free body diagram exercises. Like the first part is of the chapter deals with bodies in two dimensions. Very many applications are of this type, with all forces acting in same plane and moments perpendicular. All moments are perpendicular to that plane. Or if there is symmetry of loading, like this here plane, it's symmetric about its longitudinal plane. So we can analyze, for example, the reactions at the rear wheels grounding or at the landing gear in a two dimensional diagram. So weight of the airplane, it's acting in the longitudinal plane, and because the rear wheels share the load evenly, we just assume this to be the reaction between the ground and the wheel as two times the reaction force. Right, free body diagrams. One of the most important concepts, as I said, uh, in statics. So uh, when analyzing bodies for equilibrium, we're going to show them released from their um, assembly, and instead represent the effect of the environment, other bodies, or the ground um, with forces. So it could be um, rigid to rigid contact, or could be the effect of fluid flow, could be the effect of gravity. That's shown as weight, special type of force, or it could be magnetic electric interactions. Those two can be included as force of moments, part of this analysis. All right, so there are several examples. The most common ones, so roller contact without negligible friction. There's just the force is perpendicular to the common tangent, a contact point. The pin smooth, no friction. introduces, or as we isolate the body, remove it from its pin, we need to show a force that at some angle, or we can introduce two orthogonal forces, horizontal, vertical, x and y. And then for a fixed support, or if we analyze two parts of a rigid body, we need to introduce two forces and the moment. Okay. Everything is summarized here with some additions. So if we have a rope, ideally we're assuming the rope to be massless. So there's tension that's generated in the rope. If we have a rod, it can be in both directions, but has the direction of the rod. Rod is considered massless. Likewise, the rope. We can have the sliding contact, and there will be a force that's acting normal to the surface. This would be like an equivalent. So we have like a roller. This is a smaller carriage that can slide along. It can rotates. So yeah, this would be the force that's shown perpendicular, has the direction of the radius, and it's perpendicular to the line of sliding. And if we have smooth surface contact, we likewise show a force. So smooth contact meaning there's no friction. So we show a force that has the direction of common, normal, or perpendicular to the tangent, the contact point. We have a roller in a slot. Likewise, so find a contact point, extend the force. It should be through the pinpoint of the roller. And then looking here, it's a rod with a collar, frictionless, and a pin. So there's no resistance to sliding. I cannot move the collar perpendicular to the rod. So that's why this force. And I can't assume frictionless. I can pivot the link. So that's why there's no moment. And moving forward now, I can have a pin. We looked at this. So there will be a pin. Frictionless. So it introduces two. I'm suppressing the two translations. So we have two forces, or a force at an angle. And then I have a slide, no possibility of rotation like earlier. So these are two unknowns. So I need to introduce a force perpendicular to the direction along which sliding is permitted, and then a moment. And then lastly, fixed support. We saw that I have two orthogonal forces, the effect of the environment upon the body and the moment. And some practical examples: pin with a cable, rocking contact to allow for thermal expansion. This girder rest on beams, and then welded joints, which are fixed supports, equivalent to fixed supports. Internal forces that don't count because they are action and reaction. So any tension or compression between parts, bolted joints, or since it's an engine here, as it operates, we have the pressure acting upon the piston and the pressure acting upon the cylinder head. They too cancel each other's effect. There is a net effect at the crankshaft, though, and that's the torque that is delivered by the motor. Weight is the resultant of the parallel forces caused by gravity. So Earth is pulling every little piece of the body towards the center of the Earth, but on a small scale, those are considered parallel. If a body has geometric symmetry and it's homogeneous, then the weight, the resultant of the all gravitational forces, acts at the geometric center. And then we're dealing with you do idealizations. One, we assume already bodies are not deformable. If they deform without any resistance. Cables, springs, well, that they resist deflection, but we're assuming them to be massless. Likewise, ropes would be considered massless. And oftentimes we neglect the own weight when external loads are much bigger, is the case here. Okay, so here's an example. We have a aerial work platform. This will be the weight of the operator. It shows G, that's the center of mass of the boom. It's where the resultant gravitational force acting upon the boom are shown for the purpose of analyzing maybe the force in the cylinder BC or reactions at the joints. All right, so important points. You need to draw the free body diagram. Essentially, you remove the body, show a silhouette, you limit the amount of details, and then you show the effect of the environment, other bodies, using the rules that we learned. You identify the type of contact. Is a pin joint, is a sliding joint, is a fixed support. So if a translation is suppressed, then we have a reaction force, a rotation is prevented, we have a couple moment, and then weight, if it's relevant, and then remember, couple moments, our phi vectors should be shown anywhere. The effect upon the support, the environment is not affected by where we locate a couple moments, and forces are sliding vectors, can be shown anywhere along their line of action. All right. So again, draw the outline, show the body release from its connections, show forces in the couple moments, and then show some dimensions, and state the equilibrium equation. So here's an example. A cantilever beam with an external load, some geometry. So free body diagram, since this fixed support, we show two forces in a moment. There's no rule, but it's good to assume when we don't have any prior knowledge, we're assuming both to be positive, or not necessarily. So from calculations, if one force ends up being negative number, it means that the assumption about its orientation was not the right one. Okay. And now the examples. See, we have spring, elastic springs. We need to know their free length and the amount of deformation, spring constant, to show their effect. Or if we have round bodies contacting, they interact between themselves via normal forces, which have the direction of the common normal, that is, are perpendicular to the common tangent at the contact point. All right. So let's move to equilibrium equations, or equations of equilibrium. We can state them for two dimensions. Remember, we had them sum of vector force equals 0, sum of vector moments about a point O equals 0. So we can say sum of force in the x direction equals 0, sum of force in the y direction equals 0, sum of moments about some arbitrary point O is 0, equilibrium equations. But instead, we can state the equilibrium equations as one sum of forces and then two sum of moments about two different points. And these points have to be not parallel to the y-axis. So would be the other axis. If I have x here, it should be not parallel to the x-axis. I can say sum of force in the y direction and moments about 2 points, in that case, A and B points should not be parallel with the other axis, which would be x instead. And then the third equilibrium equation is to state all sum of moments or sum of moments about point A, B, and C equals 0. Condition for equilibrium. In strength materials, you will see we have a preference for, although the sum of forces equations are the more convenient to state, we'll prefer to use the other sum of forces for verification. All right, so part of the analysis, we need to choose a reference frame and assume some there are unknown force or moment, some some orientation to the respective force or moments, and if they end up negative, we need to reorient them on the diagram. Here's an example with a cable on a pulley. The effect of the rope or cable upon the pulley. Again, rope, cables assume massless and infinitely or very flexible, negligibly stiff. So there will be distributed force. This drawing should be identical to this one, but mirrored. And then we have a pin joint. We're assuming no friction, so we show two forces. And we have tension over the cable. It should be the same, assuming again that the cable is massless and inextensible. Right. And some more examples. Again, feel free to study them on your own. And moving forward, we have this concept of 2 and 3 force members. So we can simplify analysis if we recognize that there are part of the system, there are 2 force members. So neglecting the weight of the hydraulic cylinder compared with the loads that are developed in the cylinder. This is a 2 force member. So what is a 2 force member? One where there are only two forces acting upon the member, and they are in alignment. They don't generate a moment. So that means that this end force and this end force are equal. And then there are 3 force members where we have 3 force members or 3 forces acting, and for equilibrium, they need to be concentric, so extending their line of action, they need to intersect at the same point. Right. So yeah, recognize 2 force member. Its shape is not relevant. Could be a straight link or shaped link, like in this problem, it's L-shaped, but the as being 2 force members, this L-shaped link, the forces are collinear. All right. There are some examples, and if I remember correctly, the chapter ends, or rather continues, with systems of 3-dimensional bodies. We'll cover them in a separate recording. And some conceptual problems, testing your everyday life experience, in a sense. Okay, so I'm stopping here. Sorry for my voice. Not even 20 minutes of recording. And again, thank you.